Hello, everyone, and welcome. And I hope to many of you welcome back to another of our webinars from OpenEye Cadence Molecular Sciences. My name's Paul Hawkins. I'm Principal Product Evangelist here at OECMS, and I will be your moderator for today's discussion. I am delighted to welcome as our presenter today, or welcome back actually, for a repeat performance, my colleague Chris Neale. Chris is the head of our Molecular Binding Affinity Group here at OECMS. Prior to joining us, he was a staff scientist at the Theoretical Biology and Biophysics Group at Los Alamos National Lab. Chris has had a lot of experience in related problems in the drug discovery space, rational drug design, cell signaling to membrane proteins, task automation, and more. So he brings a lot of really interesting experience to this problem. Today, Chris is going to be presenting on our relative binding free energy prediction tool, Free Energy NES, FE-NES. So without further ado, Chris, take it away.
Thanks, Paul. OpenEye offers a variety of tools for molecular ideation and posing. Today, I'm going to talk about how we can help you rank order these predictions and make decisions about which molecules to make and which molecules not to make. More specifically, I'm going to focus on the ranking of analogs in congeneric series during lead optimization and how the explosion of accessible chemistry drives the need for methods that are fast and scalable. This talk is going to be divided into 3 parts. In the first part, I'll go over methods that we offer for triage and computational lead optimization. The second part of this talk will be about how to make these predictions more rapidly. And the third part is about expanding these pipelines so that we can access much larger amounts of chemical matter. So we like to think about these tools as existing within a conceptual funnel where the methods become more accurate as they become more computationally demanding down toward the bottom of that funnel. So up at the top, you can have your molecular ideation, followed by some posing and scoring, and a large amount of triage where we eliminate many of these molecular ideas. Can run some short molecular dynamic simulations where we look at things like the stability of the posed molecules. And again, we can triage out a number of those analogs. Then at the bottom of this funnel, we have relative binding free energy approaches where we can directly estimate the affinities at which these molecules bind to their targets. So we can actually apply a variety of scores to these different levels. At the posing and scoring level, we have access to things like the ChemGauss-4 docking score, which is very rapid. We can also do single conformation endpoint approximations to the binding affinity with methods like MMPBSA. Once we've run some molecular dynamic simulations, we can take ensemble average of these thermalized and somewhat equilibrated structures and make ensemble average MMPBSA rankings. And then in the RBFE space, we have a method called free energy non-equilibrium switching, or FE-NES. In this space of relative binding free energy calculation with physics-based methods, most approaches involve the alchemical morphing of one molecule into another molecule. So we have small molecule A morphing into small molecule B, and molecule B is the stronger binder if that transformation releases more energy when it's done in the context of the protein than when it's done free in aqueous solution. Equilibrium methods like free energy perturbation and thermodynamic integration do this by creating a variety of simulations along an ordered parameter that spans between analog A and analog B. So at lambda 0, we have a standard simulation of molecule A. At lambda 1, we have a standard simulation of molecule B. And in between, there's a number of simulations that simulate this alchemical chimeric intermediate that has some properties of molecule A and some properties of molecule B. That's done in the bound state and in the unbound state, and then that information is stitched together to give an estimate of the relative binding affinities of these two ligands. Free energy non-equilibrium switching takes a slightly different approach. We do a standard simulation of molecule A, and then we take frames from that trajectory and we drive these very rapid switches between molecule A and molecule B. These fast transformations occur out of equilibrium and are done over only 50 picoseconds. By default, we do 80 of these. We run them in the target bound state and in solution, and then we run the converse standard simulation of molecule B, and then we drive rapid transitions from molecule B to molecule A. And again, we stitch that information together to get an estimate of which of these molecules binds more strongly and quantitatively by how much. On the right is a movie of a short non-equilibrium switching simulation where we've got a small molecule in a protein binding pocket surrounded by water. And in this case, hydrogen is disappearing throughout the simulation, and in green, an alkyl cyclohexyl group is appearing through the simulation. This is the type of switch that we repeat 80 times in both directions in bound and unbound states to get that estimate of the relative difference in binding affinity. So we do this not only between molecules A and B, but between many pairs of different analogs and put that information together to get an estimate of the affinity for each of the molecules in the congeneric series. Because this is a non-equilibrium approach, it has some excellent properties for scaling on elastic cloud resources. That's because the molecular dynamic simulations at the endpoints can all be run in parallel, and then the switches between A and B, between all of the pairs of ligands, can be run in parallel. So this trajectory independence allows us to go out to a cloud provider like AWS, grab hundreds or thousands of GPUs simultaneously, run all of these switches, and then drop the compute and stop paying for it. It also provides fault tolerance, because if any one of these switches is being run on a spot instance that gets taken away, which certainly can happen, these spot instances are much cheaper, but they're not guaranteed for the duration of your simulation, we can in fact just drop that simulation out and keep going. In an equilibrium approach, one would have to wait and reobtain computational resources and then continue that simulation. Finally, these non-equilibrium approaches have some built-in sampling efficiencies by which they can circumvent some sampling barriers as they grow a larger group, where in an equilibrium context, those sampling barriers would have to be overcome in both directions multiple times. So I'm going to compare these various methods we have for rank ordering down the triage funnel. And I'm going to do that in a quantitative way by first taking for each benchmark target the experimental affinity and comparing it to the predicted affinity or the score. I'm going to do this for 16 different aqueous protein targets, each of which is associated with 10 to 50 different bound ligands in the congeneric series. And in each case, I can make the type of correlation plot that's shown on the right. And then I'm going to compress this down into a single number, which is the Kendall's tau. That's a measure of the rank association between the experiment and the prediction or the score. Larger is better, and 1 is the maximum value. A Kendall's tau of 1 means the rank order from the prediction or score is exactly the same as the rank order from experiment, and that's the type of information we need to make prioritization decisions for synthesis. So here I'm showing Kendall's tau for each of those 16 different targets in 4 different strip charts. So in each of the strip charts, for each color, each data point represents the Kendall's tau of one protein with its congeneric series of ligands. And then we're moving down the funnel from left to right on this plot. So ChemGauss 4 docking scores, their Kendall's taus are shown on the left, followed by endpoint MMPBSA, ensemble average MMPBSA, and on the right, the FE-NES predictions. So what you can see is that as we're moving down this funnel towards FE-NES, the predictions collectively are becoming more accurate and more useful for prioritization. It's also a statistically significantly better approach compared to all of these other approaches here when we look at a paired t-test. We can also then ask which of these approaches has the highest Kendall's tau for each of the 16 targets. And what you can see here is that FE-NES is the most performant in terms of rank ordering for 10 of those 16 targets, which means if you had to pick one method, it would clearly in this case be FE-NES. But it's not always going to be the best. And this data indicates that you should always be assessing the various methods that are at your disposal for rank ordering and prioritization for each target and ligand chemistry and around each cycle of DMTA. Clarify that, I can just show a plot of the Kendall's tau for MMPBSA from MD simulations versus experiment horizontally versus Kendall's tau for any FE-NES versus experiment vertically. Each point is a protein benchmark with all of its ligands. And the fact that these points tend to lie on the identity line or to the upper left indicates that FE-NES is typically the better method, but it's not always the case. I can also compare the rank ordering that comes out of FE-NES to other methods that are available to you. So again, I'm showing strip charts of the Kendall's tau for prediction versus experiment. On the left is the predictions from FE-NES. In the middle is Schrodinger's FEP plus predictions from a 2023 paper. And on the right are the predictions from Open Free Energy Consortium from their 2025 data release. And I can draw two conclusions from this slide. The first is that these spreads are quite large across all of these methods, meaning they can sometimes be very useful for rank ordering and sometimes only modestly useful. The second is if we look at, again, paired t-tests, the differences between the methods are either statistically non-significant or only very modestly significant. So there are a lot of methods available to you in this space. Moving back to FE-NES, if I look at Kendall's tau now for 20 different targets with their congeneric ligand series, this is a distribution of the Kendall's tau. I've arranged these targets in order of decreasing ability of FE-NES to rank order the ligands. And what you can see is that for 40 of the 20 sets, we've got a Kendall's tau above 0.4, which is the point at which a rank association starts to become useful across the range for molecular prioritization. So I showed you in this section that we offer a variety of tools for ligand prioritization in lead optimization. I demonstrated that FE-NES typically outperforms the other tools, but I showed that it's always worth assessing all of the metrics at your disposal because sometimes some of these simpler methods will outperform the more computationally demanding physics-based methods. So in the title, I promised ideas at breakfast and discoveries by lunch. So on the car on the way to work one day, I was trying to think about how I could demonstrate this. And I thought, well, when I get to work, I'll take the molecule of the month from the RCSB, which turned out to be the abscisic acid receptor in September. So I got in at 9 a.m. I put that PDB ID into our protein preparation tool, Spruce. I also took the molecule of abscisic acid and I ran it through our molecular ideation tool, Brood, which can generate bioisosteres, different R groups with similar shape and color. I took those molecules, which numbered over 100, and put them into our RBFE edge mapper, which picks the pairs of molecules for which we'll calculate the alchemical transformation. And by about 10:15, I had launched a job to run the molecular dynamics simulations and the FE-NES calculations. At this point, I can go do something else with my time. You can see on the bottom right, the cloud resources are bursting at one point up to 800 concurrent GPUs as they churn through these simulations. And by about 3:30, I had my results on the same day. I could start to interpret them, make decisions about what to make or what type of other triage I might do with orthogonal properties. So this is pretty amazing that I've got my results on the same day, but I think it's fair to say I didn't deliver on my promise. I didn't sit there at lunch analyzing the outputs from my FE-NES run. And the second part of this talk is about how we can get there. This is really about how we move from FE-NES into rapid FE-NES. So I showed you before that we can run all the MD simulations in parallel. We can run all the switches in parallel. And by default, we run 6 nanoseconds of MD per endpoint ligand and 80 switches per edge. Those are values we took from the literature, but they're control knobs that we can modify. And one of the ways that we can do that is, for instance, to just run a quarter of the sampling. So just 1.5 nanoseconds per ligand and 20 switches per edge. And what this gives us then is an increased capacity. We can run 3 times as many analogs for the same computational budget as we can run through default FE-NES with those settings. Of course, we're going to have to make some type of trade-off here between the number of analogs that we can put through and the accuracy at which we generate those predictions. And that's what I'm quantifying here. So I took all of the per switch values from my original benchmark simulations, and I can just reanalyze those from the beginning of the stack. So instead of just analyzing all 80 switches, I can analyze the first 60 or the first 20. And in doing so, I can compare again to experiment, and I can look at the change in the mean absolute error for the free energy predictions per ligand. And that's what I'm showing vertically, the change in mean absolute error at n switches versus the absolute error that was already there at 80 switches. So it's what you'd expect. As we move to the left, we're investing less computational effort and we're getting an increase in the inaccuracy of our predictions. But this is a really long tail. It turns out that if we drop from 80 down to 20 switches, we're sacrificing on average about 0.2 kcals per mole of additional prediction inaccuracy. So in terms of Kendall's tau, what that means is shown on the right. These are Kendall's tau FE-NES versus experiment from 80 switches horizontally, or for rapid FE-NES with 20 switches vertically. And you can see that in many cases, they're providing similar levels of prioritization. It's true that more points are towards the lower right of the line. More computation is giving more predictive accuracy, but we can still move forward with useful decisions with rapid FE-NES. What I showed you on the previous slide was a back calculation from existing 80 switch per edge data. Here I've actually just rerun a new MD set of MD simulations and a new set of edges. So on the left is our default settings, experiment versus FE-NES predictions. And on the right is this rapid 20 switch variant, where the R squared is a little lower. The uncertainty on the predictions is a little larger, but Kendall's tau is similar, and we're going to make similar decisions about which of these analogs to make and which ones not to make at a level that allows for 3 times the analogs to be put through for the same fixed computational budget. And this is really then how we get to discoveries by lunch. My job with default FE-NES was taking a little over 5 hours to run the MD and all of the switches. When I run with only 20 switches, I'm still bursting up to hundreds of GPUs, but now it's taking me a little over 2 hours to get these results. And at 12:30, I'm sitting there eating my lunch, interpreting my results. So in the second section, I reiterated the competitive accuracy of FE-NES, and I showed you how there's these control knobs that allow you to make decisions about how many molecules you need to assess, what accuracy you need, and to control the efficiency for your DMTA cycles. Third part of this talk is really about expanding these pipelines. And I'm going to do that in 2 ways. First, through FE-NES and brood ideation. Secondly, I'm going to work up some synthetic data and discuss the balance between accuracy and capacity. So rapid FE-NES could be used in at least 2 ways in your pipelines. The first is a initial triage pre-step where you search through a much larger number of analogs with rapid FE-NES, do some triage, and then run default setting FE-NES on the set of molecules that remain, after which you can make your prioritization decisions. Another way to do it is to just swap out default FE-NES for a rapid version. And that's what I'm going to demonstrate here, except I'm not going to do 20 switches. I'm going to really look for speed and capacity, and I'm going to do 5 switches with another reduction in the amount of simulation per ligand. That gives me a capacity increase from default settings of about 7.5 times. So for this demonstration, I'm going to take one ligand from the CDK8 target benchmark. On the left is the relationship between experimental affinity and default setting FE-NES predictions. And I'm showing this because this is how I picked this molecule. I wanted one that I knew the affinity could be increased and it could be decreased. So I picked something from the middle of the pack, and that's the molecule that's shown on the right-hand side. I visualized that molecule and I saw that there was some space around this methylamide, so I selected it for molecular ideation. And brood is going to generate a variety of variants that have similar shape and color in this region, but different chemistry. So that gave me about 900 different analogs. I took those analogs and I clustered them, and that resulted in 26 different clusters. And now I'm going to run 5-switch rapid FE-NES on just the representative structures from each cluster, on the cluster heads. And in doing so, I'm making the assumption that the representative structure's affinity is somehow similar to the affinity of the other molecules in that cluster. Then I'm going to take the clusters, which are predicted to bind most strongly by their representative analog, and I'm going to run another round of 5-switch rapid FE-NES on all the members of those clusters. So the parent scaffold again is on the top right, and I'm going to use a star map for this, where the parent scaffold is the hub, and all of the analogs that I'm evaluating are the spokes, where the lines represent independent relative binding for energy calculations. So here's the results of that first round. Ligand 19 is the parent scaffold. I found 2 molecules that were predicted to bind more strongly, 3 molecules that were predicted to bind more weakly, but within uncertainty. So I took all of the members of those 5 clusters into my next round of rapid FE-NES, and that's 130 molecules. In this case, I get a distribution of molecules that are predicted to have higher affinity, similar affinity, or lower affinity. Here's some examples of molecules that were predicted to have higher affinity than that parent scaffold. You can see we've got some types of similar chemistry, but we now have actually diverse chemistry at this R group. And we can use this in 2 ways. We can use this to look for molecules that have a stronger binding, or perhaps molecules that have a similar binding, but have other properties like enhanced solubility or other characteristics that we're trying to optimize simultaneously. So we didn't actually make these 130 molecules and test them, and I don't have the experimental values for anything except that parent ligand. That's what's shown as the yellow bullseye on this plot. But what I can do is quantitatively evaluate how well 5-switch FE-NES performs as a stand-in for default 80-switch FE-NES. And that's the result on this plot. So the 5-switch approach is the horizontal values. The default 80-switch approach is the vertical values. And there's a spread here, but there's a useful correlation. So all of the values in red to the left of the vertical line, that's what rapid FE-NES suggested were better than the parent. All of the molecules below the horizontal line are what default NES suggested were better than the parent. And at 7.5 times increased capacity with this 5-switch variant, I've got recovery of 75% of the top analogs that were predicted by the default settings. We could always ask, right? We have this funnel structure for triage. Why would we use something as expensive as 5-switch FE-NES? Why wouldn't we just use MMPBSA for our triage? And again, I don't have the experimental data to show you which one is better, but what I can demonstrate on the right here is that single point MMPBSA is not a useful predictor of the RBFE predictions. So you can see there's no correlation between these data. In fact, MMPBSA said almost all of these molecules were better. And a triage from 5-switch FE-NES provides value in front of or in place of a triage by 80-switch FE-NES, whereas MMPBSA is doing something completely orthogonal. In the last part of this talk, I want to focus on this direct balance between accuracy and coverage. Of course, we always want the method to be as accurate as possible, and of course, we want to put as many molecules as we can through the predicted approach, but there's a tension to this trade-off, and the real question is, where do we want to sit along this trade-off? And in order to assess that, I generated some synthetic data. That's because with our existing benchmark data, which has 10 to 50 ligands in each congeneric series, it's hard to address questions like, what if we ran 500 or 5,000 molecules through this prediction tool? So what I did was I took the real experimental values and the real predictions out of default FE-NES, and I used those to fit some synthetic data. So I can generate analogs, synthetic analogs, whose mean and standard deviation of the experimental values for affinity match the actual data, and the predictions for those synthetic analogs match the residuals, the error in the prediction versus experiment, and the way that error correlates with the experimental value. So now I can move for each of my 16 benchmark targets from 10 to 50 analogs, in this case to 10,000 analogs. I could easily make as many as I want once I have these fits. And what I'm showing you here is that in creating this synthetic data, I've maintained the approximate ability of the predictions to rank order the molecules by the experimental data. So the tau between real predictions and real experiment for these 10 to 50 analog sets is horizontally, and the taus for the synthetic predictions versus synthetic experimental data for 10,000 analogs is vertically. And I'm just going to kind of dive into one of these from the middle of the pack. This is Beta Secretase 1. And on the left is the raw data. This is the horizontal experimental affinity versus the default FE-NES predictions. And on the right is the synthetic data set with 10,000 synthetic analogs. And what I'm showing is the tau values are similar, the Pearson R-squareds are similar, the mean absolute errors are similar, but I've gone from 36 analogs up to 10,000 analogs, which is something that I can more reasonably probe for this balance between accuracy and coverage. So the thought experiment is this. I'm going to imagine that I run FE-NES on some number, n analogs. I'm going to use those predictions to identify the top 50, which are the ones I'm going to make. And then in this context, make means now I'm going to look at the experimental values associated with those synthetic analogs. And now I'm just going to pick the best one. So the question is, what's the best affinity single ligand I can find by running prediction on n analogs and then actually making 50 of them. I'm going to repeat this synthetic experiment 1,000 times for each level of n, and the values here are on the right. So n is the horizontal axis. These are the number of synthetic analogs that we're going to probe with a prediction method. And then vertically is the binding free energy of the strongest binding ligand that we found. And this result shouldn't surprise you. We have a static level of accuracy, but as we evaluate more and more analogs in our prediction, we're making better decisions. We're finding analogs whose experimental value represents a stronger affinity. So that's what I'm representing on the top here. If you have a fixed prediction error and you look at more analogs, you're going to make better decisions. In the middle, I haven't demonstrated this, but I think it's clear. If you have a fixed number of analogs, but you have more accurate predictions, of course, you're also going to make better decisions. And the real question here is on the bottom. This is the trade-off between 80 switch and 5 switch, FE-NES, for example. We can assess many more analogs, but that comes at the cost of a slight increase in the prediction error. And the question is, where along this trade-off do we reach the optimal decisions? So just going back to the real data, I need a little more data to parameterize this evaluation. This is again from Beta Secretase 1, but I did it independently for each of the sets. I can look at the relationship between the number of switches per edge, this is how much compute I'm putting into the prediction, horizontally, and vertically, the free energy mean absolute error of those ligands in that set. And this is consistent with what I showed you before. The fewer switches leads to a larger error. In this case, it's about 0.2 kcals per mole of additional error once we get down to very few switches per edge. And on the right, this is the real data quantification of the capacity, how many ligands can I put through at the same computational cost based on the number of switches. So I showed you before that if I can run n ligands through at 80 switches, I can run 3n through at 20 switches and about 7.5n through at 5 switches. So now we have all of the information that we need. We can go back to the Beta Secretase 1 synthetic data, and we can ask, do we make better decisions with a little more accuracy and many fewer analogs, or with a little worse accuracy and many more analogs? So here we've got, again, the switches per edge horizontally. And on the top of that, I've shown the ratios of n, where I've picked n to be, I'm going to run FE-NES on 500 analogs at default settings or on 1,500 analogs with 20 switches, for instance. And what turns out to be the relationship is that even as I slowly increase my prediction error, I'm much more dramatically increasing the number of compounds that I can assess at the same computational budget, and that is leading to a decrease in the free energy of binding of the best synthetic experimental data that I find. I'm making better decisions when I run my predictions on larger numbers of analogs. That was just for Beta Secretase 1. I can, of course, do that with independent fitted synthetic data for each of the benchmark data sets. That's what's shown here. Each color represents a single protein benchmark data set. As we move from right with default settings and fewer analogs to left with fewer switches and more analogs, the general trend maintains exactly what we saw with Beta Secretase. We're making better decisions as we move to look at larger numbers of analogs. So in this section, I showed you that rapid FE-NES fills a pipeline gap, either as a pre-filter or as a stand-in where you can run larger numbers of ligands. And then I demonstrated with synthetic data that you can achieve better outcomes by evaluating more analogs. And when using synthetic data trained on all of our real data from FE-NES, this favors running rapid FE-NES on larger numbers of compounds across almost all of the 16 benchmark data sets. So to summarize the whole talk, I started by demonstrating how we're improving these triage pipelines and how the methods become more accurate as you move towards the bottom, with FE-NES being our most reliably accurate approach. Second part of this talk was about how we're making these approaches faster. That was how we get to our discoveries by lunch with rapid FE-NES. And the third part of the talk was about how we make these pipelines wider, even at the lower stages where you can be looking at thousands of molecules with rapid FE-NES. And these faster and wider components are really essential in this age where we have this explosion of available chemistry that's demanding methods that are both fast and scalable. Thank you.
Thanks very much, Chris. Fascinating as always. A few questions have come in that I'd like to put to you before we let you go. Firstly, you showed fairly early on in the talk that, perhaps surprisingly to some people, something as simple as a docking score outperformed a much more computationally intensive relative binding free energy calculations. Why do you think that is? And what do you think people should take away from that observation?
So we don't ever know in advance before we run the calculations which method is going to perform the best. We do know statistically FE-NES is most likely to be the most performant method. But it's true, sometimes the docking score is the best. And I think it's a meaningful takeaway. Look at all the possible correlations you can. You already have that docking score. If this is one of those stranger, sets of ligand chemistry where that's working for you, obviously go with it. I think the addendum there is that doesn't always hold up over multiple rounds at the MTA. So it's worth reassessing whether a heavier method like FE-NES begins to provide more value as you progress your project.
Okay, super. Thank you. A striking observation you made later on the talk to several people and to me too, is you get really very good quality predictions with what feels like a very small amount of simulation. Why do you think that is?
So it surprised us too. I think the key thing here is for independent samples, the error goes with the square root of the number of samples. And with our non-equilibrium approach, we know that the work values we're getting for each of those non-equilibrium switches tends to be relatively uncorrelated to its neighboring values. And so we're getting independent samples from each one, and this scales qualitatively in the way we would expect, where you quadruple your amount of sampling and you only cut your error in half. That would not necessarily be the case for an equilibrium approach.
Right. So following up on that in two directions, a couple of sharp-eyed viewers, you showed a couple of cases where you dropped the number of switches, say, from the defaulted 80 down to 20, but you were showing about a 3x increase in throughput, but you've actually reduced the number of switches by 4x. What's going on there?
Yeah, so there's some overhead involved. There's some things we always have to do once, no matter how many switches there are. And part of it is that this is kind of relatively new directions for us. And so the things that were at the margins, not taking up very much time as we drop the number of switches, are taking a larger and larger percentage of the time. And we are investing effort now to speed up the fast things, which have become meaningful.
Right. And to stay with that briefly, you showed across a lot of different targets that what seems like a very small number of switches, 5, is working well for affinity ranking. Where do you see the place of the longer simulation with our default number of 80 or even higher?
I see that as the place that people should start. This is working for us, but you saw in the early part of my talk, and we talked about it just recently, the ChemGauss 4 score sometimes works better than our default FE-NES. And so these statistically expected results don't always hold up in a one-off, and your one project has to be guided by the things that are working for that project. So run your default settings, take your retrospective data, run 5-switch NES, and see if it provides, a similar level for you, at which point you're off to the races. You're running, almost 10 times as many analogs for the same compute budget.
Yeah, makes good sense. Forward-looking statement. Obviously, a lot of people are interested in attacking the problem of mining affinity prediction, not only through physics-based methods like at RBFE NES, but also through machine learning type methods. How do you see those two rather different approaches working together, or do you see them working together at all?
Absolutely working together in a very complementary way. Machine learning methods are great at interpolation, and FE-NES is great at, because it's physics-based, providing information in the absence of, any values to interpolate between. So we've run tests, for example, taking a retrospective data set, making a random selection of maybe a tenth of those analogs, running FE-NES, using that to train a ML model. There's obviously a variety of models. You can train those, for example, a 3D QSAR model. And then we've demonstrated that there's cases where that 3D QSAR model can make predictions that are useful for, when compared against the experimental data, which they never saw. We're purely training an ML model on the FE-NES predictions.
That's comforting. Last thing, very operational question. You showed FE-NES sort of instantiated through our cloud platform, Orion. Is it possible to run FE-NES locally?
Not with the tools that we provide. Remember, I showed you in the demonstration of discoveries by lunch, we were bursting out to 600 or 800 GPUs on cloud computing simultaneously. So that's something that takes a couple of hours on your laptop because it's doing the compute elsewhere. This is still a very compute-heavy approach. It's the elastic scaling on cloud computing that makes it seem like it's not demanding quite as much as it is.
So for now, cloud only.
For now, cloud only.
Thank you. Chris, thank you very much as always. That was enlightening. I've learned a little as you've gone along. So thank you again. Thank you everyone for listening, and we look forward to seeing you at our next webinar. Until then, goodbye.